Hello and welcome to this live stream of the OCR Breadth in Physics practice paper. This is the new specification. It's the unseen specimen paper that was created by OCR for this purpose. I hope everyone can hear me. Excuse me, sorry, I could hear my own voice going back to me about 30 seconds later. There we go. Right, so I hope everyone can hear me and is ready and raring to go as we go through this walkthrough. Welcome to Dr. Pedram, who we'll find in the chat box. He'll hopefully be responding to some of your questions. Welcome to all the people who have logged in already. I will occasionally look at the chat box, but obviously I'm focused mainly on the main screen here, which is the PDF that I'll be annotating. So without any further ado, let's start with section A. This is the multiple choice section. Remember that there are 20 marks available in the multiple choice, one per question, and you should allow no more than 25 minutes. So when you do the paper, make sure, I suggest you start with the multiple choices at the start of the paper, but make sure you keep an eye on the time. Don't allow yourself to go over that 25 minutes because although there are 20 questions, they're only worth 1 mark each. A relatively small fraction of the overall paper. There's far more marks to be gained from the main chunk of the paper, which you should allow at least an hour and 5 for. So here's question number 1. We have a man standing in a lift. He's standing on some scales in the lift, and the lift is accelerating vertically upwards with a constant acceleration given to us here of A. It tells us quite helpfully that the scales show the normal contact force experienced by the man. We need to choose what the reading shown on the scales is equivalent to. So we can represent our man on the scales with a circle there, and we can draw the forces acting on the man. So we know that we have the weight acting straight down, and that weight is equal to, right, we've got the weight acting straight down, and that weight is equal to capital M, lowercase g, capital M here being the man's mass. And we know that there is a normal contact force acting vertically upwards. We also know that the lift is accelerating with an acceleration of A meters per second squared. So we should know from our studies that resultant force F is equal to the difference between the two forces we've got here. So if these two forces were perfectly balanced, if the normal contact force was equal to the weight, then there would be no resultant force. We know that there must be a resultant force here because there's an acceleration. So we therefore know that this normal force must be a bit larger than the weight here in order to provide that acceleration. So the resultant force is going to be equal to the difference between the normal contact force acting upwards from the scales and the weight acting downwards, capital Mg. Now we want to find what that normal contact force is because that's what the scales will show. So we can rearrange here to get N equals F plus Mg. And we know that F equals ma. That's one of our most important equations, Newton's second law. So we can replace F here with capital M, because that's the man's mass, A plus Mg. And then we'll see that if we factorize that, we'll get capital M and in brackets A plus G, which is answer C. It was quite a tricky question, actually. It's talking about the power rating of a toaster is 2,000 watts. Which of these is not an equivalent power rating? So it's not really a question about power or electricity. It's a question about dimensional analysis, about units. These is an equivalent unit. Well, let's work, or rather, which one is not an equivalent unit. So we can start here with 2 times 10 to the minus 9 terawatts. So we can start, we know that 2,000 watts, if we were to put that into terawatts, we'd have to multiply it by 10 to the power of 12. So, sorry, 10 to the power of minus 12. Divide effectively here. We're dividing by 10 to the power of 12, which is the multiplier of the terawatts. So 2,000 watts is equivalent to 2,000 times 10 to the minus 12 terawatts, which we can simplify to be 2 times 10 to the power of minus 9 terawatts. So that's correct. So A is equivalent. So we're looking for the one that's not. Let's try B. We've got 2,000 Newton meters seconds. Now here, the number is 2,000. That's fine. We just need to see whether Newton meters per second is equivalent to the watt. So if we make some space over here, Newton meters per second, sorry. Well, we know that a Newton meter is a force times a distance, which is a work done. That's equivalent to a joule. So if we were to divide work done by time, that would give us a unit of Newton meters per second, which must be a unit of power, because that's work done divided by time. So this one is also correct. It is equivalent to a watt. 2 kilojoules per second. Well, a joule per second is a watt. A kilojoule per second would be 1,000 watts per second. So that is 2,000 watts. So we can tick that one's correct. So it must be the last one that's incorrect, but we can demonstrate that that's the case. 2,000 millijoules is actually equal to, 2,000 millijoules per second is actually equal to 2 joules per second, which is only 2 watts. So that's no good. That's the incorrect one. So our answer is D. I see a couple of questions asking why terawatts was 10 to the minus 12 here. I should apologize. To convert from terawatts, to convert from watts to terawatts, you would normally divide by 10 to the power of 12. So that's the same as multiplying by 10 to the minus 12. That's where the minuses come from here. If you did it the other way around, if you multiplied by 10 to the 12, you'd get an enormous number. And that, converting something to terawatts, which is a big unit, you expect a smaller number. So you'd run that through a sanity check. Question number 3, which of these statements is correct, is true about electromagnetic radiation? Well, the first one here, radio waves are in the highest energy range of the electromagnetic spectrum. Well, we know that's not true. We know that radio waves are actually the lowest energy, the lowest frequency, and the lowest energy. So that one is false. Visible light has a range of wavelengths in the order of 450 nanometers to 700 nanometers. Well, we should know roughly visible light is in that order. So that one is the true one. We'll have a look at the other two in a second. It's just something you need to remember that visible light is measured in hundreds of nanometers, and actually it's between 450 and 700. Ultraviolet waves cannot be plane polarized. Well, that's just plain false, because we know that ultraviolet waves are a form of electromagnetic radiation, and all electromagnetic radiation can be polarized, so that's just not true. And gamma rays have a low frequency. Well, no, that's not true. Gamma rays are the highest energy and the highest frequency of the electromagnetic spectrum. So our answer here is definitely B. Moving on to question number 4. The force constant of a spring is 1.2 newtons per centimeter. And we've got 4 other spring characteristics here, the force extension graphs for 4 other springs. We need to say which one has a force constant that's equal to half of spring X. So half of spring X would be 0.6 newtons per centimetre. Well, first little hurdle they have here is that the extension has been given to us in metres. We're more interested in centimetres here because our initial one's been given in centimetres. So that's 5 centimetres. That won't be 10. That's 15 centimetres. And that's 20 centimetres. Now, what we need to do to find out the force constant is you divide it by extension. In other words, you find the gradient of each of these lines. So I'll just demonstrate the first one for that. We know that F equals Kx. That's one of our formulas from the formula sheet. And we know that K, therefore, is F divided by X. That is the gradient of the line. So for the first one, for spring A, we'd see that that would be 12 newtons divided by 5 centimeters. We're working in centimeters here, even though it's not an SI unit, simply because that's what this has been given. The other way around of doing it, of course, would be to convert this to newtons per meter and stay in meters all the way through. And that gives us a value here of 2.4 newtons per centimeter. Now, that's not the one we're looking for. We're looking for 0.6. I'm not going to go through and show you how to calculate all of them, but B, you'll find comes out as 1.2. C comes out as 0.6, so that's the one we want. That was 0.3, so our correct answer here will be C. Moving on to question number 5, which order of magnitude here gives the best estimate for the wavelength in meters of microwave radiation just beyond the infrared part of the electromagnetic spectrum? So what's basically it's asking roughly what is the wavelength of microwaves, fairly high frequency microwaves, the microwaves that are closer to the infrared. So this is actually, it might not look at first glance, it's actually quite a difficult question. And it requires an awful lot of kind of general physics knowledge about the electromagnetic spectrum. So you should be aware that when we're talking measured in meters here, that if you've got radio waves that are measured in meters or even in kilometers, as 10 to the 3 would be, then we would be talking about radio waves. Okay, so radio waves are the only types of waves that are measured in meters or even kilometers. The bottom here, 10 to the minus 6. Now that 10 to the minus 7 would be, as we saw in the previous question, hundreds of nanometers. That would be sort of visible light. 10 to the minus 6, but it's probably too close to that. So it's infrared, quite close to visible, which means that the only one it really can be would be 10 to the minus 3. That would give us a much shorter wavelength. Sorry, a much longer wavelength than. So the answer here is C, but it's not easy to come to that answer by any kind of quantitative method. You just need to have a good idea about the electromagnetic spectrum and the various lengths. Question number 6, we've got a sheet of A4 paper held horizontally and dropped from rest on the top of a tall building. It falls towards the ground below, reaching terminal velocity on the way. The same piece of paper is crumpled into a small ball and dropped from the same height. It also reaches terminal velocity. Which of the following will change in the second situation? The first one says the maximum magnitude of the air resistance. Well, air resistance, the magnitude of air resistance is at a maximum when it reaches terminal velocity. And in that case, terminal velocity is reached when the drag is equal to the weight. Now, both pieces of paper here have the same weight. So the maximum drag for both pieces of paper must also be the same. So that statement is incorrect. The weight of the paper, well, we've just said that there's nothing has changed about the paper. It's just been crumpled up. The mass hasn't changed. G hasn't changed. So weight stays the same. M and G are both constants. The time taken to reach terminal velocity. This is something students often struggle with. The reason why, when we're dropping things in the fluid as air, that a heavier object will appear to fall, well, it does fall at a faster rate, is because a heavier object requires more drag to cancel out its weight. So if we have a light object with a small weight, it only needs a relatively small amount of drag to cancel that out. With a larger object, a more heavy object that has a larger weight, you need a larger drag. The object reaches terminal velocity. That means the ball will have to fall for longer and until it's reached a higher speed before that drag builds up enough to cancel out the weight of the heavier object. Now, in this case, of course, sorry, the paper hasn't changed its weight, but it has changed its dimensions, which means that greater drag will build up on the not scrunched up, or rather, a greater drag will be required for it to reach terminal velocity. Actually, sorry, that doesn't make sense, does it? The ball that is scrunched up will reach a higher terminal velocity, which means that it will fall for longer before it reaches terminal velocity. So this statement C is correct, if I've not explained that very clearly, perhaps. And D, the initial acceleration, will know the initial acceleration is fixed, that is G equals 9.81 meters per second squared. That is a constant. So even if you weren't quite sure about how to explain step C here, it's the only one that can be true. So we would go for answer C. The best way of looking at it, sorry, is that you've got your paper unscrunched. It will reach terminal velocity very quickly because it's got such a large surface area. It will generate a lot of drag very soon. Whereas the smaller piece of paper, the crunched up piece of paper, will take longer to accumulate the same amount of drag because it's smaller. Ultimately, they will both reach the same amount of drag because their weights are both the same. Question 7, we've got a copper wire connected across a cell. The electrons within the copper are moving. Which of these statements is correct? So A, the electrons drift towards the negative end of the cell. Well, that's impossible because the electrons themselves are negatively charged. They will be attracted to the positive terminal, so that's incorrect. The electrons have got random speeds because of collisions with many electrons. Well, no, that's not true. The reason they've got random speeds is because they're colliding with ions, not with other electrons, so that isn't correct. Speed of light, no, that's also not correct because the only thing that can travel at the speed of light is light. Even electrons can't travel that fast. Although the signal, the effect of you switching on an electrical supply, that may effectively pass by at the speed of light. The electrons themselves are not moving anywhere near that speed. And finally, part D, the electrons collide with vibrating copper ions. Well, that is true. That's what we just said. That's what resistance is. It's electrons colliding with ions. So that's C. By the way, just a reminder that if you've got any questions, if I'm not making something clear as I'm going through this, please do leave a message in the chat box. Dr. Pedram's in there. He will, if he can, and if I, every now and again, I'll stop and I'll have a look in the chat box myself and I'll respond on the video as well. Also, a reminder that this video will be automatically uploaded to YouTube immediately afterwards, so you'll be able to browse backwards and look over anything you didn't quite understand the first time and hopefully get it again. On to question number 8, we have a light-emitting diode and a resistor connected in series to a battery of negligible internal resistance. It tells us the EMF of the battery is 8 volts, and we have a charge of 10 coulombs passing through the resistor. Sorry, a charge of 10 coulombs passing through the resistor will transfer 60 joules of energy. What is the potential difference across the LED? Well, we don't have enough information here to directly calculate the potential difference across the LED, but we do know all about the resistor. We do know enough about to work out the potential difference across the resistor. We have an equation on a formula sheet. We know that the voltage is equal to the work done divided by the charge. That's the definition of the volt. The volt is joules per coulomb, so this makes sense. We've got work done divided by charge. We know that 60 joules of work is done by 10 coulombs of charge, which means that 6 volts is the potential difference across the resistor. So that is 6 volts. So 8 volts is being put into the circuit of EMF. 6 volts is coming out as potential difference across the resistor, which must mean that the remaining 2 volts are being dropped across the LED. So our answer here is A. This is an example of Kirchhoff's second law, where the EMF into the circuit is equal to the sum of the potential differences coming out of that circuit. Question 9, the initial temperature T1 of water in a beaker was 20.1 degrees C plus or minus 0.2 degrees. After the water had been heated, the temperature was 27.3 plus or minus 0.3. The temperature increase is given by change in temperature, delta T, is T2 minus T1. What is the best estimate of the uncertainty in delta T? Now this is not really a question about thermal physics or anything like that. This is a question solidly about uncertainties, and you need to know the rules about uncertainties. I've got a video about this that you can look at on my channel if you search for uncertainties. For combining uncertainties when you are adding or subtracting values, which is what you're doing here, you're subtracting 2 temperatures, one from the other. The rule is that you add the absolute uncertainties. By absolute uncertainties, we mean these values here, the 0.2 and the 0.3. So 0.2 plus 0.3 gives us 0.5 degrees C as our absolute uncertainty, which is this one. So the answer is D. Let me just demonstrate what that means in practice. The lowest possible, let's say 27.3 was actually 0.3 high, which is the maximum range there. So that would be 27.6. Take away 19.2, which is the lowest possible value there. That would give you a value that is 0.5 different from if you just directly subtracted 27.3 and 20.1. So the maximum difference at the end of the calculation is 0.5. Question 10, we've got a ball here thrown at an initial angle. This is a projectile motion question. Air resistance is negligible. That's always the case in projectile motion questions. Which correct variation of the ball's horizontal velocity with time t? Well, you should know 2 rules about projectile motion, or at least 2 rules about projectile motion. The first being that the vertical, you have constant v, sorry, constant a even. In the vertical direction, you have a constant acceleration, usually due to gravity. And in the horizontal direction, you have a constant v, a constant velocity. No matter, and the two components are independent of each other. So no matter what's going on in the vertical direction, the horizontal motion will always be a constant velocity. The only one of these graphs here that represents a constant velocity is C. So our answer is C. Question 11, we have a water pipe that has some pressurized gas in it, and it's caused the water to move up on one side, causing a height difference. Now the pipe isn't vertical, so use these equations as correct. Now there is an equation on your formula sheet to work out P equals rho G H, where rho is the density, G is gravity, and H is the height. Now you can't use this directly here because this H is not vertical. So I'm going to use a capital H to represent the actual height. So we can draw a triangle here, the right angle triangle, the actual vertical height, capital H, lowercase h there, and we've got the angle theta. So capital H, if you do some trigonometry, you'll find is equal to lowercase h cos, which means that the pressure is equal to rho G H cos theta, which would be this one here, answer C. There's nothing more complex than that. It's simply using the equation that's given to you on the formula sheet and recognizing that the height has to be the vertical height, so finding the vertical height. Question 12, we've got a girl standing on a bridge, throws a coin upwards, vertical velocity of 5 meters per second. It hits the water below the bridge after 1.5 seconds. Again, assuming air resistance is negligible, what was the height of the coin above the water originally? Now, this is one of those questions where you really do have to put all of your trust in Suvat. So this is our starting position where S, the displacement, is 0. We're going to say that vertically upwards is our positive direction. So the coin goes up and it comes straight back down again. So this is where we just have to have complete faith that by putting in the right numbers at the start, Suvat will give us our answer. So let's write out what we know. S, well, that's what we're trying to find out. We want to know what S is, and we should expect a negative number to come out because we're looking for the distance, the displacement below this starting point, and I've said that upwards is positive. Our initial velocity, U, do we know that? Yes, we do. That's the 5 meters per second. V, we don't care about. We're not interested in V. The acceleration, now be careful here, the acceleration is negative 9.81 meters per second squared. The reason it's negative is because the acceleration is acting down, and we've said that positive is up. And T, we know it takes 1.5 seconds. So you can choose your Suvat equation. You want the Suvat equation that does not have V in it, which would be S equals UT plus half AT squared, and we can plug in all of our values here, and eventually this would come out as being minus 3.5 meters. Now we expected that minus sign, which means that answer B is the correct answer. Question 13, we've got a question about stationary waves. We need to know a couple of rules about stationary waves that are being set up in tubes. When tubes have an open, then that would give you an antinode. And when they're closed, that will give you a node. In this case, the tube is open at both ends, which means that we have to have an antinode at both ends. So B cannot be correct and D cannot be correct. So is it A or is it C? Well, the question tells us that a flute is played so that it sounds the next harmonic above the fundamental frequency. The smallest pattern that you could produce a full, sorry, that would give you half a wavelength would be the pattern there in A. So that would be the fundamental with the antinode, the node, and the antinode. We're interested in the next harmonic above that. So that must be a wave that looks more like this. Which is wave C. We have an antinode at each end, and we have half a wavelength there in the middle between the two nodes. The full length of this standing wave here is 1 wavelength, which tells us that it's the first harmonic above the fundamental, which was only half a wavelength. Question 14. By the way, about 5 minutes ago, we passed the we passed the time limit for the first 20 marks. Obviously, I'm going at a slower pace than you would need to go in an exam. Question 14, a sodium lamp is rated at 40 watts. For 12% of the power is emitted as yellow light of wavelength 5.9 times 10 to the minus 7. How many photons of light are emitted per second? The first thing we need to do is work out how much energy each of these photons would have. To do that, we need to use the equation E equals hc divided by lambda, Planck constant, speed of light, and the wavelength, which gives us 6.63 times 10 to the minus 34, multiplied by 3 times 10 to the 8, divided by 5.9 times 10 to the minus 7, which gives us an answer of 3.37 times 10 to the minus 19 joules for each photon. Just a quick tip here, if you're ever looking at for the energy of a photon, it will usually be around about 10 to the minus 19. If you've got some value that's way off that, then the chances are you've made a mistake somewhere in your calculation. So now let's just consider 1 second of time. So because the power is 40 watts, in 1 second, that means the energy is 40 joules. And we need to multiply that by 12%, by 0.12 of that energy that is actually being emitted as the yellow light that we're interested in, because only 12% is being emitted as yellow light, which means that our energy here is actually 4.8 joules. We now need to find out how many times we can fit this tiny number here, 3.37 times 10 to the minus 19. That's the energy of one photon. How many times we can fit that number inside 4.8, and that will give us our 4.8 divided by 3.37 times 10 to the minus 19, and that gives us 1.42 times 10 to the positive 19. And again, you run a sanity check here. How many photons? Photons are emitted by the trillion. This is times 10 to the power of 19. It's a huge number. It should be a huge number. If you've got a small number, especially if you've got a number less than 1, then you've made a mistake. So our answer here is A. We have a beam of monochromatic light passing from air to glass. The speed of the photons is 3 times 10 to the 8 in the air and 2 times 10 to the 8 in glass. So which of these is correct? The energy of a photon in the glass is 1.5 times the energy of the photon in the air. Well, the first thing we need to remember here is that E equals hf. And when a photon changes speed, it does so, keeps its frequency constant. So if the frequency is constant, that means actually the energy, well, if this was a particle with mass, obviously then the kinetic energy, half mv squared, that would be different if the velocity was different, but this isn't. This is a photon. It has no mass. It's traveling at the speed of light, two different speeds of light in this case, but it means that is unchanged, so its energy is unchanged. So this one that talks about the energy being bigger is wrong. This one that talks about the energy being smaller is wrong. This one also is. The only one that's correct is the one that acknowledges that the energy is constant. So that is B. Question 16 is a rather tricky question. What is the best estimate for the density of steel? Now, the way I approach that is by using what I know. I know that water has a density of 1,000 kilograms, 1,000 kilograms per meter cubed. Is equal to 1. We can convert that, sorry, into grams per meter cubed. So that would be 1 times 10 to the 6. So it's 1 times 10 to the 3 kilograms per meter cubed, 1 times 10 to the 6 grams per meter cubed. And then by dividing that by 100 cubed, because 100 is obviously the factor for centimeters, and we're talking about centimeters cubed, so divide that by 100 cubed will finally give us an answer gram per cubic centimeter. Those of you who do chemistry may already be familiar with that unit anyway as the density of water. So when we're talking in kilograms per cubic meter, our water is 1,000. We're talking in grams per cubic centimeter. Water is just 1 gram. We know that steel will have a density greater than water because obviously steel sinks in water. So some of these values are now 10 to the minus 3. That's 1/1000th. That's 1,000 times smaller than the density of water. So it definitely can't be that one because steel is heavier than water. The second one here, 10 to the power of 3 grams per centimeter, that would be 1,000 times heavier than water, 1,000 times more dense. Now that, yes, steel is more dense than water, but is it really 1,000 times more dense than water? Would you need tons of water to weigh the same as 1 ton of steel? So that doesn't make sense. You need 1,000 cubic meters of water to weigh the same as 1 cubic meter of steel. That's not true. It's not 1,000 times. 1 kilogram per cubic meter, that is 1,000th again of water, so that also can't be right. Which leaves us with the last one, which is roughly equal to the density of water, 10 to the power of 3. So even though it's not got exactly the same density as water, the approximate best estimate would still be the same value. The answer is D. Just for interest, obviously you wouldn't have been able to do this in the exam, but I did look up what the density of water is, and it's 8,050 kilograms per cubic meter, which is obviously 8 times 10 to the 3. So 10 to the 3 is a reasonable estimate. Excuse me. On to question 17. We have a graph showing displacement against time for a progressive wave, and we need to say which of these statements can be deduced from the graph. So the first one here, the frequency of the wave is 5 hertz. Well, we can't directly read frequency from a graph, but we can calculate frequency. We know that frequency is equal to 1 divided by time period. And we know that time period here is 0.2 because we're measuring from here to here. That is one full oscillation of the wave, and that is taking 0.2 seconds, which gives us frequency. Away, we can say that actually the answer is A. That's the correct one. But let's just have a look at the other ones. The graph represents a transverse wave motion. We can't necessarily say that because although it looks like a transverse wave on here, you could represent the displacement of a longitudinal wave using a graph like this, just by plotting the displacement of it against time. So we can't say that that's definitely true. The amplitude is, well, amplitude is the maximum displacement from the equilibrium position, and that is 6 millimeters. So it's true that from peak to from the bottom of the wave to the it's 12 millimeters. So that's not how we determine amplitude. Amplitude is only 6. The wavelength is 60 meters. We can't deduce that at all from here, because to work out wavelength, we'd need to know the speed, because we'd have to use the equation v equals f lambda. We know the frequency. We want to find out the wavelength. We don't know the speed, so we couldn't do that. So the only one is A. Should be a straightforward question. A lot of students struggle with this one, but it boils down to knowing some of the rules of parallel circuits. We've got 2 batteries in parallel, both of them 6 volts, and 2 resistors in parallel as well. So effectively, we've got just 4 components all in parallel with each other. At this stage, it's worth remembering exactly what voltage is. Again, I'll refer you to one of my videos. It's called Voltage and Current, in which I use an analogy to explain exactly what current and voltage are. But remember that voltage is the energy per coulomb. 6 volts means that at this stage here, you have 6 joules per coulomb, and it also means that here 6 joules per coulomb. So each coulomb of charge is carrying 6 joules. The fact that these combine together here, yes, it will mean that there are more, or there could be more coulombs, but each coulomb is still only carrying 6 joules. The potential difference hasn't changed. So it's still 6 joules per coulomb, 6 volts. Obviously, when we get around here, again, that's the same thing is true. Although the charge is split, per coulomb, so each coulomb of charge is still just carrying 6 joules of energy, and the same, and then that energy is given up in the resistor. So that on the other side here, each coulomb of charge is carrying no joules of energy, and here no joules of energy, and obviously then all the way back here, no joules carried by each coulomb. So the question here, what is the voltage across each resistor? Well, 6 joules per coulomb, that is 6 volts. 0 joules per coulomb is 0 volts. So the potential difference measured across here would be 6 volts. I mean, that was a very long-winded way of explaining exactly what's happening, but the rule is that the very definition of what a parallel branch is, that all parallel branches are at the same potential difference. All of these branches here have to be at 6 volts. (19). We have a ray of light that's bending twice here as it passes through 3 different mediums. Which of these statements is correct? So statement A, the velocity of light in medium 3 is equal to the velocity of light in medium 1. Well, that would only be true if theta 3 was equal to theta 1. We've got no indication here that that's the case. So in that case, that's not true. Let's if I could demonstrate that perhaps by using Snell's law. So we know that n1 sine theta excuse me, is equal to a constant, or another way of saying that would be that n1 sine theta equals n2 sine theta 2. And you can then rearrange that. You would get n1 over n2 is equal to sine theta 2 divided by sine theta 1. We also know that the refractive index n is equal to the speed of light in a vacuum c divided by the speed of light in that medium v. So n is proportional to 1 over the velocity, which means that we can replace n1 over n2 here by v2. So that ratio is just the other way up is equal to sine theta 2 divided by sine theta 1. Now what you'll see here is if we then multiply both sides by v1, we'd get v2 equals v1 sine theta 2 divided by sine theta 1. What we've got here, this has skipped a stage, it's gone straight to v3, but if you worked through the maths, you would see that the same thing holds true. So v3 equals v1 times sine theta 3 divided by sine theta 1. So that one is true. Let's have a look at the other ones. The frequency of light in medium 2 is less than the frequency. Well, that's not true. We established in an earlier question, frequency is constant. Finally, n2 over n1 equals v2 over v1. We set it up here that n is proportional to 1 over v. So actually, no, n2 over n1 is equal to v1 over v2, but the other way up. So that one is wrong. It has to be b, even if we're not quite sure about the whether we can go straight from n1 to n3. And finally, question 20 from the multiple choice section. We have 3 springs that have been attached, 2 in parallel, 1 in series, and we're asked to find out the distance moved by it. Now we've got a graph here that tells us the force extension characteristic, one of those resistors. We can use that, as we did earlier, to do K equals 20 divided by 0.5, which gives us a spring constant of 40 newtons per meter. So we know what we're working with now. So this one is 40, this one is 40, and this one is 40. Now, the rule here is that it's for combining springs is that actually it works in the opposite way to what you know about how to combine resistors. So here we've got 2 in parallel. If that was resistors, then we'd have to use the 1 over 40 plus 1 and so on. Here, because this is springs, it's the opposite. It's the same rule as it would be for series resistors. So we simply add them. 40 plus 40 gives us 80 newtons per meter. Now, just pause for a second and again, kind of run a sanity check through this. It makes sense that 2 springs in parallel would feel stiffer. You'd have to apply more force to extend them than just 1 spring on its own, which makes sense here. We've got a bigger spring constant, therefore a higher stiffness. So 80 for that. And then we need to combine that 80 with the 40 here. And to do that, we do need to use the equation similar to resistors. So combining springs in series is like combining resistors in parallel. 1 over k total is equal to 1 over 80, which is our combination up here, plus 1 over 40. And that will come out as 26.7 newtons per meter. We can then use F equals kx, rearranging to get x, F divided by k, which gives us 60 over 26.7, which is 2.25 meters. And fantastic, that must be answer C, correct to 2 significant figures, 2.3 meters. That's the end of the multiple choice section. That's taken us exactly twice as long as it should have done. Obviously, you would need to work a lot faster than I have, and you wouldn't need to be explaining it as you're going through and so on. But allow 25 minutes for that section. Now you're into section B. which is where 50 out of the 70 marks are awarded. So very important last few questions to complete here. Question 21, a crane raises a mass of 3,000 kilograms through a height of 12 meters in 40 seconds with an efficiency of 60%. What's the total input energy to the crane? So the first thing we can work out here is what the output energy is. And the output energy here is a result of lifting the mass through a height and it gaining gravitational potential energy. So that would be equal to 3,000 times 9.81. 3,000 is the mass times g 9.81 multiplied by the 12 meters it gains. And that comes out as 3.53 multiplied by 10 to the power of 5 joules. So that's our output energy. We know that efficiency is equal to the output divided by the input. And we can rearrange that then to get the input, which is what we're interested in, is equal to the output divided by the efficiency. So that would be 3.53 times 10 to the 5 divided by the efficiency, which is 0.6, 60%, and 5.89 times 10 to the power of 5. Now, remember that answers through a sanity check, you should expect a bigger input than output. Obviously, you can't put in more energy, so you can't put in less energy than you get out, but you can put it in more energy than you get out because there's inefficiencies in the crane. So that seems like a sensible answer. B moves us on to a question more about materials. The crane cable is an alloy. Here's the stress strain curve for it. Use the graph to estimate the stress in the cable at its elastic limit. Now, the elastic limit is reached in this section of the graph here. We've got a straight section here where we can see that beyond that, it begins to disobey Hooke's law, and in reality, you're getting sort of plastic deformation going on in this region as well. So the elastic limit is somewhere around here. There's a little bit of margin of error here. You could move a little bit lower, a little bit higher, but it should be around about 230 megapascals. A very common mistake students would make here is to say that that is the elastic limit here, but it's not. That is the ultimate breaking stress. It's not the elastic limit. Actually, it's the, yeah. II, a cable of diameter 0.09 meters has a maximum working load allowance of 1.1 times 10 to the 6. By calculating the maximum tensile stress allowed, suggest and explain why the working load allowance is 1.1 times 10 to the 6 newtons. So it gives us a big hint there. We need to calculate the maximum tensile stress, so we'll start by doing that. We know that stress is equal to force divided by area. The force is 1.1 times 10 to the power of 6. And we need to calculate the area. So we need to use pi d, pi times the diameter squared, divided by 4. So pi times 0.090 squared divided by 4. And this should give us a stress of 173 joules. Now, first thing you'll notice that 173 megapascals is less than 230 megapascals. So it's lower than the elastic limit. That means that lower than the elastic limit, so the cable will not deform plastically. On to question 21. We are faced with another spring here, and this spring has a natural length of 20 centimeters, and a mass is attached. It oscillates for a short while and then settles in a new equilibrium position. So we've got unstretched at 20 centimeters, fully stretched at 25. We need to calculate the change in the gravitational potential energy of the mass when it finally comes to rest in its equilibrium position. So the change in the gravitational potential energy here is due to a change in the height. So gravitational potential energy is equal to mass times g times the height. We know the mass of the block is 6 kilograms. Multiply that by 9.81. Multiply that by the change in the height. So this is a very common mistake. Students would use 25 centimeters here. The change in the height is only 5 centimeters. It's 25, or 0.25 meters. Take away 0.2 meters. And that works out as 0.29 joules. And part B, we need to show that the elastic potential energy in the stretch spring is 0.15 joules. So the equation for elastic potential energy, there's two equations on your formula sheet. This one is that half Fx is equal to the elastic potential energy. So 0.5 multiplied by the force acting, which is here is mg. So again, 0.681. Again, multiplied by that change tension x, 0.25 minus 0.2, a elastic potential energy of 0.147 joules. This is to show that question, so you better well show all of your working to get the marks. Now, a student has looked at these two values and noticed that they're not the same. The gravitational potential energy gained is 0.29. Sorry, the gravitational potential energy lost is 0.29. The elastic potential energy gained is 0.147. So the student compares these and says that energy hasn't been conserved. Now we know from from physics that energy is always conserved. So the student has to be wrong here. Otherwise, this experiment is defying the laws of physics. So the first thing the question says is state the energy transfers that occur as the spring oscillates. A lot of students, when they've attempted this question, simply don't state those energy is falling. The mass is falling. Gravitational potential energy is being converted into elastic potential energy plus kinetic energy. And the spring is rising back up again. Remember, the spring here is oscillating backwards and forwards. That elastic potential energy from the stretch spring is being converted back into gravitational potential energy and again kinetic energy. How come not all of it is being converted by the time it reaches comes to rest? Well, the reason for that is that some energy is being dissipated as heat as a result of friction or drag. That's the key thing there. The student is wrong because energy is being conserved. Some of the energy is being lost as heat. Question 23. Question 23 is a very difficult question. It's something that wouldn't have been asked even in a year 12 paper in the old spec. It's using knowledge that's related more to the to year 13. So use ideas about momentum to explain why the water splashes in many directions. There's got water vertically traveling down and then splashing in lots of directions as it hits the ground. This is a question about conservation of momentum. So the first thing we need to do here is separate it out. So between vertical and horizontal motion. If we just consider the horizontal motion only, we can say that the initial momentum is 0, as the water is flowing vertically going sideways, so it's got no horizontal momentum. And we know also that momentum must be conserved. That's a fundamental law. Momentum has to be conserved. So if there's 0 momentum in the horizontal direction before the water hits the ground, there must also be 0 momentum of the water after it's hit the ground. So if some of it splashes to one side, you must have an equal and opposite amount splashing to the other side to balance it out and ensure that the overall momentum still remains 0 in the horizontal direction. So a similar example, by the way, to this question about momentum is a firework that explodes. Firework, you could sit a firework on a table and set fire to it. It would have no momentum at the beginning. Momentum has to be conserved, so that means that every bit that explodes to the right would also have to explode to the left, and so on, in order for momentum to be conserved. Part B continues the theme of the water puddle, but this time it's more about light and polarization. So first of all, explain what is meant by the term polarized waves. You may wish to illustrate your answer with a labeled diagram. I'm not going to use a diagram, but feel free to do so. The definition of a polarized wave is a transverse oscillates or vibrates in only one plane. That would be enough for 2 marks. Part 2 says, describe how the student can use the polarizing filter to determine if the reflected light from the puddle is partially polarized. State clearly what she should observe. So this is an experiment you may have done in class using Polaroid filters, polarizing filters, in which you take a polarized source and you rotate the filter around. And as you'll see, that as you rotate the filter around, when it's aligned with the polarized light, all of the light will be transmitted, or most of the light. And when it's 90 degrees around, if it's perfectly polarized, none will get through. If it's partially polarized, some will get through. So here we're talking about it being partially polarized. So the first thing you need to do is rotate the filter. Light should vary in brightness, rotating bright and dim every 90 degrees. It won't go completely dark because it's partially polarized, not fully polarized. So some unpolarized light will always get through. Question 24 is very much a kind of ideas about science, practical skills question, which we're looking at a couple of paper planes, the condor and the piranha. An experiment's been done for both, where they've been fixed velocity from a catapult from the same height, and it's been repeated lots of times. They've measured the time of the flight with a stopwatch. First part of this says to state 2 ways the student could ensure this is a fair test. Well, there's lots of options you can say here, but first of all, make sure that the mass of the paper planes is equal every single test, and to make sure that the angle that the paper planes are launched at is also equal. There's a couple of more answers you could have, but those are 2 pretty solid answers. And using figure 23.2, state the minimum and maximum flight times for the piranha. Now, this is perhaps the easiest question I've ever seen in any kind of A-level paper, and I'd be surprised if they gave you anything quite like this in the exam. So looking at the piranha column, what is the minimum time? Well, it's not a trick question here. The minimum time is 1.6. And the maximum time is 2. And using figure 23.2, determine the best estimate of the condor's flight time. Include a suitable uncertainty and give your values to an appropriate number of significant figures. Now is an appropriate time to discuss significant figures. Normally, you should give all your answers to 2 or 3 significant figures, but if the question, as this one does, put number of significant figures, then you need to think about it a bit more deeply than that. I'll go through what that means in a second. First of all, let's look at our data, knowing that it's just up the screen from us. So looking at the condor, we have 3.5, 3.9, 4.2, 3.4, and 1.8. Now, the first thing you'll notice is that 1.8 is clearly an outlier. Handling our data correctly, we should exclude that outlier when we're calculating our best estimate. So we will find the average of 3.8, 3.9, 4.2, and 3.4. Do that by dividing by 4. We've excluded the outlier. We haven't included that in our calculation, and we get 3.75 seconds as the mean. Now, we're not going to write that down here yet, but what we haven't thought about is what an appropriate number of significant figures will be. So we'll come back to that in a moment. But the uncertainty we need to give as well. When we're dealing with repeated results, the uncertainty is driven by the spread of the results. So you do that by calculating half. So in this case, the maximum value is 4.2. The minimum value is 3.4. Divide that by 2, and that will give us 0.4. So the range of the results is 0.8. Therefore, the uncertainty is half the range. That's 0.4. So we know that uncertainty is 0.4. Now, what's an appropriate number of significant figures to use for the flight time? All of our values here have been given to 2 significant figures. It would be wrong of us to use 3 significant figures for our answer, so our answer should also be given to 2 significant figures. So that would be 3.8. And part D, the student concludes that the condor has a greater horizontal range than the piranha because the condor's flight time is longer. Explain whether you agree with that conclusion. You can use data to support your answer. Having looked at the mark scheme for this, what OCR we're looking for with this question is 3 things. That's what the 3 marks are for. It actually doesn't matter whether you agree, disagree, or not sure, as long as you include some sort of statement one way or the other, back up that statement, and kind of a therefore, what is the outcome of that of that data. So for example, I've chosen to say that the student is correct because distance equals speed times time. So greater time, greater distance. That means we've got our statement, the student is correct. We've got our data, that D is equal to VT, and we've got our outcome. Greater time means greater distance. As I say, you could have equally talked about a few other examples. Have a look at the mark scheme to see what those other examples would be. Question 25. We have a wafer of semiconductor, which is has these dimensions that are given to us here. So suggest how the thickness of the semiconductor was determined. Now this was a question that initially seems quite easy, but actually, if you look at the mark scheme, they're very picky about it. Yes, you need to use a micrometer, but you need to take repeat readings using a micrometer. Enough because the semiconductor could have an uncertainty, and in fact, you can see that's evident here in the measurement. So part B, the wafer is connected to a power supply. The current I in the wafer is 32 milliamps. Potential difference is 0.13. Show that resistivity rho is given by this expression here. So we know from our equation sheet that R is equal to rho L divided by A. So we could rearrange that to get rho equals RA divided by L, where L is the length of the conductor. Now, we have to be careful with some of our terms we're defining here. So we know that R can also be written as V divided by I. Cross-sectional area of our conductor here is this surface here. So that is L times L, which is L squared, capital L we're talking about here. Meanwhile, the lowercase l that's used in our equation is the length of the conductor, which is actually this dimension here, the thickness. So lowercase l is equal to T. So we can now substitute these values back into our equation. So rho equals V divided by I multiplied by L squared over T, and that's correct. That's what we predicted we'd get up there. But II, the resistivity of the semiconductor, we now need to just plug in these values. So rho equals 0.13, the voltage, multiplied by 25 times 10 to the minus 3 squared, divided by 32 times 10 to the minus 3, 32 milliamps, times 0.6 times 10 to the minus 3 equals 4.23 ohm meters. Part C, the ammeter reading increases when the circuit in B remains connected. Use your knowledge of semiconductors to explain why. So semiconductors, unlike conductors and insulators, when you increase their temperature, they actually lower their resistance. But that's because they gain free electrons when the temperature increases. This reduces the resistance, causing higher currents. Higher currents cause the semiconductor to heat up. So it's kind of a loop. It goes on and on and on. It will get hotter and hotter up to a point. And on to the penultimate question, 26. A bubble of gas rising to a glass of lemonade. We need to add arrows to the diagram first to show the forces acting on it. What it doesn't say here is that the arrows should be drawn sort of to scale, but you do need to do that for the mark. So I'm going to draw a short arrow there for drag, and another one here for weight. And I'm going to draw an arrow that is bigger than both of them combined to represent the upthrust. The reason I've done that is because we know that the bubble is accelerating upwards, which means that the upwards force must be bigger than the combination of the downwards forces. So that would get you 2 marks. Here we have the graph showing the vertical velocity of the bubble against time. And we have to use figure 26.2 to describe and explain the motion of the bubble between 0 and 3 seconds. So I'm just going to zoom out a little bit. So in the first part of the graph, we can see that it is increasing. In other words, it's accelerating. At the start, the upthrust is greater than the drag plus the weight. As the V increases, the drag increases. When the upthrust eventually, drag will increase to the point where the upthrust is equal to the drag plus the weight, or net force. Therefore, constant terminal velocity. So initially the bubble is accelerating. The rate of that acceleration decreases as the drag increases because the net force is getting smaller. Eventually you'll end up with no net force at all when the upthrust is equal to the drag and the weight. That's terminal velocity, and the bubble will continue rising at a constant. So use figure 26.2 to estimate the initial acceleration. Well, to do this, you should take a tangent on the graph. So you need to draw a line at a tangent of roughly the gradient at the start here. Triangle as big as you possibly can, following that gradient, and it should come up somewhere around about here. And you can then take a triangle here, so you'd end up with the change in y divided by the change in x being 0.009 meters per second divided by 0.5, which gives us an answer of around about 0.018 meters per second squared as our acceleration. So that's just taking a tangent of the graph because the gradient of a velocity time graph is the acceleration. So the tangent will be the acceleration at that point. And I calculate the initial upthrust U on the bubble, given the mass of the bubble is 6.7 times 10 to the minus 9. So the key thing to remember here is at the beginning of the journey, as we described before, there is zero drag, which means the only forces acting on the bubble weight down and the upthrust up. And we know that there is an acceleration, so therefore there is a net force. This is very similar to the question we attempted right at the beginning of the question in the multiple choice section. So we can say the net force F is equal to the difference between the upthrust going upwards and the weight acting downwards. We rearrange that, the upthrust is equal to F plus mg. F equals ma. Net force F equals ma, so ma plus mg. And just as we got in the earlier question, that factorizes to m multiplied by a plus g. Now we can plug in some values for this. 6.7 times 10 to the minus 9 multiplied by 0.18, sorry, 0.018, which was what we calculated earlier, as the acceleration initially, plus 9.81, which is g. So of 6.88 times 10 to the power of minus 9 newtons. Now, sorry, minus 8 newtons. And you should be careful with this question because it's a very badly written question. Actually, they wouldn't allow this in the real exam, I suspect, because if you missed out considering A here, if you just worked it out as mg, you actually get an answer that's pretty much the same. But in a real exam, that wouldn't pass. So you need to make sure that you do this properly. Finally, question 27. An open air concert, 2 loudspeakers are 5 meters apart at the front of the stage, and they're producing a note of the frequency 1200 hertz. A row of seats is 30 meters from the stage and parallel to it. This is a young double slit experiment, albeit one that's using loudspeakers instead of the slits. So we can use our equation lambda equals ax over d in order to work out some of the properties. But first of all, let's describe what's happening. So the young double slit experiment, you're going to get an interference pattern on the screen, or in this case on the row of seats. So along the row, volume will vary, getting louder at the maxima and quieter at the minima. Constructive interference, we're now explaining why this happens. Constructive interference occurs at the maxima, destructive at the minima. And it asks what happens as you go along the row. Well, as you go further along the row, the effect is less noticeable. Amplitude received from the 2 speakers become more different, so that they're superposing less. But in the center, the 2 amplitudes are very similar. But if you skew off to one side or the other, one of the speakers will become dominant over the other one, so you lose the interference effect that you would get in the middle. So it does say with a calculation. So we should do a calculation here to work out what the spacing is between the loud and quiet, what it sounds like between the fringes. So we learn that lambda is ax over d. We could find out x by rearranging that. We get lambda by a. Now we don't know lambda, however, we do know the frequency and the speed of sound, so v equals f lambda. That should be a lambda there, not really well drawn. So lambda equals lambda equals v divided by f. So 330 divided by 1200. And that gives you a wavelength of 0.275 meters. And we can then feed that into our calculation here. So 0.275 by the distance from the stage to the screen, stage to the seat, so that's 30 meters. And divide that by the spacing of the speaker, which is 5. And finally, that will give us a fringe separation of 1.65 meters. So that will get us the 4th mark here for doing the calculation. Now that's the end of the question paper. That's taken us actually just under an hour and a half, which is the time that should be expected. And bearing in mind, I spent a lot longer on the multiple choice section than. So even explaining it, we've come in under time. Obviously, you'd need a bit more thinking time in the exam when you're faced with the questions for a first time. Certainly, this isn't the first time I've seen these questions, so I didn't have to have that thinking time. I'm going to spend a few minutes now answering any questions that you may have. Okay, just looking at the first couple of questions that I've spotted in the chat box here. Will there be any walkthroughs of the OCR B practice papers? Sorry, no, there won't be, because I teach the OCR A spec. The rules of EMF sources in parallel and in series. I suppose what you're referring to there is similar to Kirchhoff's second law. So if I just sketch in parallel here, to repeat a bit of what I said earlier in one of these questions, the voltage here is constant. So the voltage across that branch is equal to the voltage across that branch. So actually, if you connect a resistor across here, that resistor will have the same voltage no matter how many batteries we put in parallel here. The same is true as if we put in loads of resistors. So anything in parallel, same voltage or same EMF. However, in series, you would add up the EMFs. So if this was 3 volts and this was 3 volts, you would effectively have 6 volts there by putting batteries in series. If you open up a remote control, you'll see inside the TV remote control, you'll see that the batteries are actually arranged in series so that you're building up a sufficient voltage to power the remote control. If you had, yeah, that's a good question about what if there are different EMF values. If these two in parallel had different EMFs, that would become rather more complicated. You would end up with one of the batteries actually charging the other or trying to charge the other. You'd have the current flowing into one of them. It's something you could solve with a more complex Kirchhoff second law question, but it's not something I would be too worried about for AS level. Just having a look back through some of the other questions here. Yeah, there's a question here that Sahel Patel has put on about the setup for the young double slit experiment with the loudspeakers. What could you do to ensure that the two waves arrive in phase? One is to connect to the same signal generator. The other is to ensure the same polarity in the wires. What that means is that both speakers are connected to the positive side of the speaker connected to the positive terminal of the signal generator and the negative to the negative. Because it's an AC wave, if you had one of them the wrong way around, it would end up producing a wave that is perfectly in antiphase to the other wave. That's the reason that's important. I can see lots of discussion. If you have any more questions, please now. I will be going through the depth paper closer to the time. I think I've got it scheduled already if you look on my live feed videos. Resistance of semiconductors decreases when current increases because more free electrons are available. I'm not sure you need to be able to explain why the semiconductors release more free electrons, but it is to do with it's quite complicated chemistry that's going on in the materials, so you don't really need to go into any detail about that. That's a good question about why the intensity. I'm assuming that's to do with the previous question. Why does the intensity decrease the further you go away? That's because a wave spreads out as it goes away from a source. So Hilbert has asked which values stay the same for different materials such as Young modulus and so on. Well, is a constant, although it's only true of materials while it's up until it's reached its elastic limit. Resistivity is a constant again, but that's only true when temperature is constant. How would I qualitatively define resistivity? It's a property of the material that dictates I suppose the ability of the material to resist the flow of electrical current independent of its length or its area. Prince, I assume you're asking about the double slit experiment or the one with the speakers at question 27. Why do the amplitudes vary? Well, when the two waves meet perfectly in phase, which would happen bang in the middle, they interfere constructively, so you'd get effectively double the original amplitude. But if you go slightly to one side, one of them will arrive half a wavelength after the other one, so they arrive in outer phase, in antiphase, out of phase with each other. But, the two waves will now cancel each other out, so it could become almost zero. And then as you go along the row, the effect becomes less and less because one of the speakers becomes dominant, and that tends to cancel out the effect. So yeah, at the maximum point, you would expect almost double the original amplitude, double if it was perfect. A couple of questions here about waves reflecting at the end of an open tube? That is a very good question, and I'm not sure it's one I've got a particularly good answer to. It's obvious why a wave would reflect at the end of a closed tube, but why it happens at an open tube, I'm going to have to pass on that one. A polymeric material, you can define best using a graph. If I do a quick sketch of the graph you'd expect to see for a polymeric material, it's going to look something like this. The key thing is it's going back to its original length here. This is a stress strain graph. It could also be a force extension graph. It's going back to its original extension, which means that it is obeying Hooke's law. But the key thing here is this area in the middle. So when you're loading the material, it follows this path. When you're unloading, it follows this path, which means that the area underneath the first curve, the energy you're putting in when you're stretching the material, ends up being less than the energy you get back out when you release the material. And that's because some of the energy is lost as heat. That's due to the polymers inside the polymeric material stretching past each other, rubbing past each other and causing friction. Could I explain the photoelectric effect? It's not one that's come up in any of these questions. The photoelectric effect is when light photons of radiation are able to knock electrons to a higher energy level inside a material, or even to allow an electron to escape a material altogether. So for that to happen, the individual photons need to have sufficient energy. It's evidence of the particle nature of light. So you get Sahel's question here about diffraction. You get the kind of the maximum diffraction when the wavelength is roughly the size of the gap. If the wavelength gets much smaller than the gap, I think you would still get some diffraction. If it gets a lot bigger than the gap, that's when you wouldn't get diffraction. Okay, I'll take questions for a couple more minutes. If you've got a question, you ask it now. Why does water speed up in a ripple tank when you increase the depth of the water, and why does speed decrease as depth is decreased? I think that's beyond yeah, it's not an explanation I could give you right now, but I think it is quite a fairly straightforward explanation, but not one I've got off the top of my head. It's certainly beyond air level. Okay, thanks very much. If you do think of any more questions, please feel free to tweet me, Cowen Physics, or you can comment on any of my videos. I've got a couple of hundred videos going through a few exam papers you can have a look at as well as videos explaining various topics. I'll take the one last question that's just come up here, actually, sorry, is Young modulus dependent on length? No, it's not. It's independent of length. That's one of the factors that goes into it. That's why Young modulus is better than the spring constant, which is what you could use alternatively. Okay, thank you very much for tuning in, and I will end the broadcast now.